In this video, let us solve the exercises that we were about to do in the last one regarding the first chapter that we have studied, that is functions on Euclidean spaces. So the chapter is not yet over and we already have solved one problem. The one problem we solved was to prove that I equals to 1 to n mod of xi is greater than or equal to norm of x, where obviously x belongs to r to the power n. This was already done. Now let us see how do we prove the other ones. Another variant of this problem is this, where we have x minus y's norm equals to mod x minus mod x plus mod y. We want to find out when the equality holds. It's basically less than equals to. So when does equality hold? So let's try and construct a proof for it. Well, obviously, if norm of x minus y is less than or equals to norm of x plus norm of y, this is something we need to prove first. Let us see. So let x equals to x1, x2 all the way up to xn, and y equals to y1, y2 all the way up to yn. Then x minus y is simply x1 minus y1, x2 minus y2 all the way up to xn minus yn. So what we see here is this: mod of x minus y whole square is simply, let us write it in terms of components. It is simply I equals to 1 to n xi minus yi whole squared, right? And this would give us I equals to 1 to n xi square plus I equals to 1 to n yi square, and there would be minus 2 I equals to 1 to n xi yi, correct? So this thing in general tells us that, well, obviously this is mod x square, this is mod y square, and this is mod x square, this is mod y square, and we need to prove that this is equal to. So obviously this is minus 2 I equals to 1 to n xi yi. Now obviously this would be less than equals to mod x square plus mod y square plus 2 times I equals to 1 to n xi yi. This has to be true, and that is why we can say that this is equals to mod x plus mod y whole squared. Therefore norm of x minus y is less than equals to norm of x plus norm of y. So this is one of the problems. Let's do the next one. This one is a bit tricky and we shall try to understand what the problem means. And we would like to prove the following. So integration of f dot g, the norm of that should be less than or equals to a to b f square to the power half into a to b g square to the power half, right? Now well, obviously equality holds when we have the integral as the integral of one function is a linear multiple of another function. So if for all lambda belongs to R. So if f and g are this is basically another Cauchy squares inequality type problem. So if for all lambda belongs to R, we have lambda f minus g whole square greater than 0, then since the integrand is positive, we can say that a to b lambda f minus g whole square is greater than 0, right? Now since this happens, so we understand that this has no real solutions, and if you expand it, it is basically lambda square into a to b f square minus 2 lambda a to b f dot g plus a to b g square greater than 0. And obviously, since this equation has no real solutions, its discriminant must be negative, right? So the discriminant d is equals to 2 into a to b f dot g whole square minus a to b f square into a to b g square, and this should be less than 0. So taking the positive square root, we find it should be 4 AC obviously, so it just should be a 4. Therefore taking the positive square root, we find a to b f dot g, the mod of which should be less than equals to a to b f square to the power 1 by 2 a to b g square to the power 1 by 2. So this should be our required result, and the equality parts comes from the fact that f and g are multiples. That is, if lambda f minus g whole square equals to 0, then obviously a to b lambda f minus g whole square equals to 0. And well, since now if it has this inequality part, then obviously we can say that it has like multiple roots, and that's why the discriminant is equal, or the discriminant should be 0, which would give us the given result. That is, evaluating this part would give us a to b f into g should be equals to a to b f square to the power half into a to b g square to the power half. This happens when f and g are linear multiples of each other, or g equals to f lambda. So this is another problem. Let us move to another one. The derivative of a function f of x at x equals to a is given by f dashed of a equals to limit x tends to a f of x minus f of a whole divided by x minus a. So this is the definition of derivative of a function, and we can use it to our advantage to find the different derivatives. Now let us begin by solving different basic derivatives first, and then we can do the other ones later. So what are the derivatives that we are going to find? So trigonometrical identities are a great way to start off this list of chapters. So trigonometrical identities. Trigonometrical identities are a better way. So the derivatives which we are going to find is sin x and cos x. So let us begin by one of them. So sin x, let f of x equals to sin x, then the derivative of f of x is, so now we try to find the derivative using first principles, and it won't be that much hard because as we have already encountered this kind of problems before, we shall be accustomed by now to as to how to approach this kind of problems and how to solve the particular limit. So here, as you can see, the question asks us for f of x equals to sin of x. So the limiting definition would be limit x tends to a f of x minus f of a by x minus a, right? Another definition for the limit is what I am going to write now, is the definition what we are going to use while solving the problems. This is limit h tends to 0 f of a plus h minus f of a divided by h. This is a more standard definition of derivatives, and I think this is more useful than the other one, because the first one is usually the one where we convert from limit to derivatives, but this one actually helps us to find the derivatives in terms of the functions, elementary functions, directly from the limit. So using the value of f of x, we can write this as like this, right? Now we can use the formula using the formula for compound angles, that is, we can add and subtract angles inside sine, and we can also express them. So we can use the formula sine of a plus b equals to sin b cos a. So this is the formula, right? So using this formula, we can see that sin of a plus h similarly would be now. When this is done, what we can do now is we can find the limit L. Actually here we do not read the answer L, we already have a name for it. So f dash a is equals to limit h tends to 0 sin a cos h plus sin h cos a minus sin a divided by h, right? So what we can do is limit h tends to 0 sin h by h into cos a. So we can just take the second term here, and we can take the first term common, and we can write limit h tends to 0 1 minus cos of h by h, right? So this limit is 1, so it becomes cos of a, because we have learned about the limit x tends to 0 sin x by x in the previous videos. And the next one, sin a into, now we first use the formula for 1 minus cos theta is equals to 2 sine square 2 by theta. So using that formula, it becomes minus 2 sine square h by 2 by h, and this limit goes to 0, because firstly sine h by, if it was sine h by 2, we could have found the answer, but since it is sine square h by 2, it goes to 0. So the answer is cos of a. So the derivative of sine of x at the point a is cos of a, right? Okay, we can do a similar calculation for cos of x as follows. So case 2 is, now the derivative would be defined as follows. Defined as follows: f dash a would be equals to limit x tends to a f of x minus f of a by x minus a, from which we can substitute h equals to x minus a to find the new definition which was more useful to us, which is like f of a plus h minus f of a divided by h, right? Now this would give us limit h tends to 0 cosine of a plus h minus cosine of a whole divided by h, right? So this means now we have to use the formula now. Trigonometry that cos of a plus h is equals to cos a cos h minus sin a sin h. Using this formula, what we can do is as follows. Using this, we have f dash a equals to limit h tends to 0 cos of a cos of h minus sin of a sin of h minus cos of a divided by h. So we can again distribute it as follows. Take cos of a common and we can write it as limit h tends to 0 cosine of h minus 1 by h minus sin of a common limit h tends to 0 sin of h by h. As we know from the previous example, this limit is 0, so this is 0 minus sin of a into 1, because this limit is 1 as we have done in previous examples. So the answer becomes minus sin of a. Okay, so that's the derivative we were trying to follow. A third example now could include the derivative of e to the power x. Derivative of e to the power x. So let f of x equals to e to the power x. Then let us evaluate the derivative at the point x itself. So what we are going to do is we are going to write it like this: h tends to 0 f of x plus h minus f of x divided by h. Okay, so this tells us limit h tends to 0 e to the power x plus h, because f of x is e to the power x. So f of x plus h would be e to the power x plus h minus e to the power x whole divided by h. We using the rule for indices, the law of indices, we can write this as e to the power x into e to the power h minus e to the power x whole divided by h. Now we can take e to the power x common as the limiting variable is h, so e to the power x is basically a constant here. We can write e to the power x into limit h tends to 0 e to the power h minus 1 divided by h. And as we know from previous experience, this limit is again equal to 1 as I have proved. So the answer is e to the power x. And as you can see, the derivative of e to the power x is e to the power x itself, which actually means that we can find the derivatives very clearly here, and this is the only function whose derivative is itself. Now once we are clear with the basic definitions of how to find derivatives, I can give you a list of basic functions and their derivatives. So let me write it down. List of common functions and their derivatives. So now I'm going to write down all the functions and their derivatives, and from the next video onwards we would be trying to implicate them and learn more about the chain rule. Okay, so the more we learn about the chain rule, the better. Okay, so derivative is usually written as d dx, where x is the derivative variable, and in bracket we write the function which we are differentiating. So this is the format that I am also going to use. So these are the three functions. Firstly, d dx of x to the power n is n into x to the power n minus 1. d dx of ln of x is 1 by x. d dx of a to the power x is a to the power x into log of a. Number 4. Is a to the power x. Number 5. Number 6. Of tan x is basically equals to sec square x. Number 8. d dx of cot x would be equal to minus cosec square x. So I think these are some of the basic things, and there are other things as well that you need to know, but for the time being this should do. This should actually work pretty well. So let me write down some more rules. If fx and gx are two differentiable functions, then d dx of fx plus gx is equals to d dx of fx plus d dx of gx. So basically, if you are given to find out the derivative of the sum of two functions where both of the functions are differentiable, then the answer is basically the derivative of the first function added with the derivative of the second function. Similarly, if you are given something like this, where you have given the multiplication of two functions, then what you can do is try this. And finally, if we are given two functions in the form of division like this, then the answer is simply gx whole squared gx into f dashed x minus fx into g dashed x. And obviously here g of x not equals to 0. So these are the three rules also that you need to follow when solving for derivatives. And along with this, the most important theorem of all is the chain rule, which we shall do in the next lecture, where after that we can be free to evaluate any derivative we want by hand. It's a magical rule, so evaluating derivatives won't be a problem anymore once you learn and once you get a hang of that rule. But before that, you need to be very much confident about all these formulas. You need to memorize them by heart so that you can just tell them at your lips. The chain rule states that the derivative of a composite function where f of x is continuous for all x belongs to u, where g is a function such that it goes from d to u, and g is continuous and differentiable at x belongs to d, then the derivative of the function f of g of x is given by f dash of gx multiplied by the derivative of gx. So it might look that it's not such a big result, and okay, the definition might be a bit more complex, but the result itself says that the ddx of f of gx, considering all the other technicalities solved, that f is continuous at g of x and f is differentiable at g of x and g is differentiable, we can say that the function f of gx can be differentiated by just differentiating the function f at the point g of x and then just differentiating g of x at the point x and multiplying them together, right? But this simple definition is the key to solving all of derivatives problems, as you can see now. So if you remember the basic derivatives, which I can recall one by one, it's like x to the power n is n into x to the power n minus 1, sin x is cos x is minus sin x and stuff. Then logarithm of x is 1 by x, e to the power x is e to the power x itself. Now we can try and find out the derivative of. So we are going to do a bunch of problems now. So let us do ddx of e to the power ax. So ddx of e to the power ax. So first recall the basic function. The function, what it starts with? It starts with the function e, right? E to the power something. Now what is the most basic representation? It's e to the power x. So if you remember, ddx of e to the power x was e to the power x, right? So we are going to copy this and write the answer itself. That is, the answer should be whatever is given. So e to the power ax, right? So pretend as if this function was e to the power x only and write the whole function down, but then multiply it with go to the next level of the function where the anomaly is present. So it should have been e to the power x, but it isn't, right? What is there instead of x? It's a of x. So now it should be ddx of ax, where a is just a constant, and when you do a constant x, a times x, the ddx of x is just 1 and constant just comes out. So the answer becomes a into e to the power ax. This is because ddx of x is just 1, and also ddx of a constant c times any function f of x is just c times the derivative of the function. So the constant just remains multiplied throughout. Okay, next example. Because the more examples we do, the more it would be easier for you to understand. ddx of ln of, let's say, x squared. So how do we do this? Well, first we try to think what the ddx of ln of x is, because the first function is ln of x, right? So ddx of ln of x is equals to 1 by x, right? So pretend as if this function is ln of x, and we write the derivative as 1 by x square. So do not directly write 1 by x, because you just need to pretend. But when you are going to write the derivative, you are going to write the same thing, and instead of x, whatever is present, you are going to use that. But you are just pretending it is x, right? Now you multiply and you do the derivative of the next level, the expression which is present instead of x. So x square is present here, so we do x square. So it is 1 by x square into ddx of x square by the rule for differentiation of powers is 2 into x to the power 2 minus 1, right? So it will become 1 by x square into 2x, which will give you 2 by x, right? Okay, one more. Let us try to evaluate ddx of log of sin x. Now, how many layers are there? Let me just clarify this like this. Layer 1 is the first layer of function. This is log. So layer 1 is log x. And what is layer 2? Layer 2 is sin x, correct? So it is log x and it is sin x. Now, the answer can be written directly if we have that in mind, because we differentiate one by one, and we keep on doing that until we reach the inner bottom where x is present. So ddx of log of sin x is simply equal to, firstly we do the ddx of log x, which is 1 by sin x, and then we do the differentiation of sin x, which is cos x, right? And cos x by sin x is simply cot x. So you see, we have got the answer. ddx of log sin x is just cot x. Okay, so this is not really a very hard one to be done. Let us move to other examples. We need to find the derivative of this function. So here comes the harder ones, or rather you can say the more complex ones, because if you know what to do, I do not think this would be at all hard for you any more than it for the last problem was. But then again, this would be a bit more calculative, right? So we first need to understand the layers and stuff. So what is layer number 1? Layer number 1 is of course sine of x, right? Sine and some x inside it, which we are going to pretend is x. Layer 2 is of the form fx by gx, right? Layer 2 is of the form fx by gx, which we learned before, that the derivative of two functions can be evaluated how? I'll just write it down here, that ddx of fx by g of x can be evaluated as fx into g prime x, right? What is layer number 3? So in fx there are two layers, right? In fx there are two layers. How many layers are there? Fx has a layer which says that the inside function is x square plus 2. Similarly, gx has a layer which says that the inside function is e to the power 5x plus e to the power x, right? But these layers do not really matter because we already have a fx by gx thing here, right? So we are going to use them here directly. So let's do this. Let us first define the function as capital F of x equals to sine of, let me just copy it, log of x square plus 2 divided by e to the power 5x plus e to the power x, e to the power 5x plus e to the power x. Then f dash x would be, so firstly the derivative of sin x is cos x, so we first have this right, multiplied by, now we have the part where we do actually fx by gx thing. So this is gx, this is fx, so this should be squared. Squared means multiplying by 2 in the power, which is e to the power 10x plus 2 e to the power x. Then we have e to the power 5x plus e to the power x into the differentiation of log of x square plus 2. So first we pretend it's a log of x, so we do a by x square plus 2, and then we do the inside, which is x square plus 2, differentiating which you get 2x because the differentiation of a constant is 0. And if you remember, addition of two functions when differentiated is basically equal to derivative of the first function plus derivative of the second function. So here derivative of the constant is 0 and derivative of constant of x square is 2x, so 2x minus ln of x square plus 2 plus remains like that. And now we do the exponential. So firstly the exponential remains the same, so it's e to the power 5x plus e to the power x multiplied by, we do the 5x plus e to the power x, which is 5 plus e to the power x, so 5 plus e to the power x. So we can write it clearly here, cos of ln of x square plus 2 by e to the power 5x plus e to the power x multiplied by, now we can do a simplification here, x square plus 2 into e to the power 10x plus 2 e to the power x, and we can write it as follows: e to the power 5x plus e to the power x taken common, we have 2x minus x square plus 2 into ln of x square plus 2 into 5 plus e to the power x, and we can cut off this 5x plus e to the power x and this to give you the final answer, which is cos of ln of x square plus 2 divided by e to the power 5x plus e to the power x into 2x minus x square plus 2 into 5 plus e to the power x into ln of x square plus 2 whole divided by e to the power 5x plus e to the power x into x square plus 2. So this is our final answer, and obviously some multiplication in between. So this is our final answer for the problem. Let me write down the problem first. preserving mod of dx equals to mod of x. Dx comma dy to x comma y. So we have like two parts to prove for this problem. So I have given you the definition of what is a norm preserving and what is a inner product preserving linear transformation. Now let us see what we have to prove. So these are our two questions that we are going to prove. So let us understand the question first. It basically means that let t from r to the power n to r to the power n be a linear transformation. It is norm preserving if norm of t of x is equals to norm of x, where x is any, let's say, vector from r to the power n, and inner product preserving if the inner product of tx and ty is equal to the inner product of x and y itself. So you understand, we just remove the t, that is why it's called preserving, because it preserves the vector itself. So taking the doing inner product or normally the norm on the transformation does not change the result if you were to do it on the vector itself. In the first part we want to prove that if t is norm preserving if and only if, which IFF means if and only if, t is inner product preserving. This means you have to prove both ways, that if t is norm preserving then it is also inner product preserving, and if t is inner product preserving then it is also norm preserving. Let us try and do the first part. So proof of first part would be like this. Okay, so we understand that given xy belongs to r to the power n, let us assume that t is norm preserving. Okay, so let t be norm preserving. That is, so we can understand that mod of norm of tx should be norm of x and norm of ty should be norm of y. So this is what we mean by norm preserving, and we need to prove that it is inner product preserving. So therefore inner product of t of x and t of y, this inner product, now we know how inner products work, right? We understand how inner products work, and it is basically the multiplication. So we understand that the inner product is basically given by the polarization identity as follows: t of x plus t of y whole squared minus t of x minus t of y whole squared by 4. This is the polarization identity, and since t is a linear operator, that means this becomes t of x plus y whole squared minus t of this would be norm x minus y whole squared by 4. Now since it is norm preserving, as we have already assumed, t of x plus y's norm would be x plus y's norm, so it should be x plus y's norm, and this should also be x minus y's norm divided by 4, and this is again the polarization identity but for x and y, so it's basically x comma y. Right, so therefore if t is norm preserving, it is inner product preserving. Well, that part is proved. Now let us assume the opposite. So now let us assume t is inner product preserving, right? T is inner product preserving, and so we are assuming that t is inner product preserving, and we are trying to prove that, and for xy belongs to r to the power n, we will be given for this one that tx comma ty's inner product is basically x comma y's inner product, right? Now we need to prove that it is norm preserving. So we know that norm of tx, as we have known before, is basically root over of inner product of tx, square root of inner product of tx with itself. And since you know that inner product of itself, since t is like norm preserving, this is equals to x comma x. This is since tx comma tx equals to x comma x, and we know this is equal to x mod x, so which is norm of x. Therefore t is norm preserving if t is inner product preserving. So this completes our proof for the first part. Now let us look at the second part. We need to prove that t is 1 1, and we also need to prove that t inverse follows the same properties as before as t. So since t is from r to the power n to r to the power n, and we understand that if t is norm preserving or maybe inner product preserving, because one of them implies the other, then obviously what we can say is that mod of tx equals to, I mean norm of tx is norm of x, which means it is onto, now for xy belongs to r to the power n such that x not equals to y, we have, let us prove it is 1 1. To prove it is 1 1, what we need to do is we need to find out if t of x equals to t of y implies the same thing. So this would mean that t of x minus t of y equals to 0. It's a linear operator. It would mean t of x minus y equals to 0, and this would mean, since t of x minus y is equal to 0, and we know that this means that the norm of t of x minus y will also be 0, and this will mean that norm of x minus y would be 0, and we know that if the norm of vector is 0, therefore the vector itself is 0, which would imply x equals to y. So it is 1 2 1 1. So it is 1 1. Since it is also onto, then it is bijective, because it is both 1 1 and onto. It is bijective, and therefore t T inverse exists, T inverse only means that T inverse of T of x is basically equal to x. Now we need to prove the same property, so we can see that T inverse is non-preserving because T inverse of x, this thing, but because T inverse of x also belongs to r to the power n, so this is basically a vector in r to the power n, and since T is non-preserving, we know that for every x, norm of x is T of norm x, right? So this should be equals to T of T inverse x, and this should be equals to norm of x. So norm preserving. Similarly, we can write T inverse of x and T inverse of y's inner product as, we know it is inner product preserving as well, the T. So for every x comma y whose inner product is also equals to the inner product of Tx comma Ty, so we can treat this as separate vectors p and q, let's say, and we can write that since pq belongs to r to the power n, this is equals to Tp comma Tq, because inner product preserving, right? And Tp comma Tq then again is equal to T of T inverse x and T of T inverse y, and this would be equal to x comma y. So T inverse is of the same sort, and we are proved. So this completes another problem. Now let us do this problem where we have which problem number was it again? It was problem number 4. So we are going to do number 5 now. Number 5 is basically and it has the matrix which is A equals to now we have to show that T is angle preserving. So show that T is angle preserving and if x not equals to 0, the angle between x and Tx is theta. So T is angle preserving means, so obviously if T is angle preserving, then it means that let me write it in the proof. If T is angle preserving, it means that angle between not like this is mostly the sign of inner product. So like this, Tx comma Ty, angle between Tx and Ty is similar to angle between x and y, and the angle between two vectors is only given by arc cos the inner product of x comma y divided by mod x into mod y, as we all know. So basically for x comma y belongs to r to the power n, we have the angle between x and y is simply given by arc cos inner product of x comma y divided by norm of x into norm of y. Okay, so for xy belongs to r to the power 2, we have so t of x should be equals to cos theta sin theta minus sin theta cos theta into x1 x2, right? And this would imply it is equals to, so it's a 2 cross 2 matrix and this is a 2 cross 1 matrix. So obviously the result would then be a 2 cross 1 matrix, which is x2 cos theta plus x1 sin theta, and this should be x2 cos theta minus x1 sin theta. This should be our tx, and we understand from this part that we can write the norm as follows. The norm would be whole squared plus x2 cos theta minus x1 sin theta whole squared. So what we can do here is we can write this as root over of, well, a plus b whole square plus a minus b whole square. It's basically 2 times a square plus b square, so 2 times x2 square cos square theta plus x1 square sin square theta, something like this. This is required, so we are just proving it. So our actual goal is to prove that t is angle preserving, which means we need to prove that angle between tx and ty is equal to cos inverse tx comma ty divided by, we have norm of x, basically norm of tx norm of tx multiplied by norm of ty, right? So in order to do that, what we need to understand here is that cos inverse of inner product of tx and ty needs to be found, and we also need to find out if tx and ty are inner product preserving and non preserving as well. So if they are any one of those, we shall be done, right? If they are any one of those, we should be done. So let's see if they are any one of those. So norm of tx is basically norm of the, and now tx basically means we are multiplying the matrix with the vector x1 comma x2. So with the vector x1 comma x2, and we understand that a here is equal to right. So and x should be equal to therefore, as we already see, that ax should be equal to and this should be equal to right. So therefore norm of Tx is basically equal to square root of x1 cos theta whole squared, not actually this much, it's basically the whole thing whole squared, plus x2 sin theta whole squared plus x2 cos theta minus x1 sin theta whole squared. Now if you were to expand this thing, what you would get is the as follows, because the 2ab and minus 2ab terms are the same, they will cut off, and what you would get is x1 square bracket cos square theta plus sin square theta plus x2 square bracket sin square theta plus cos square theta, and this would give you root over of x1 square plus x2 square, and 6x is a vector in R2, this is basically equals to norm of x. So T is norm preserving, so T is norm preserving, therefore it is also inner product preserving, therefore it is also inner product preserving from the last exercise. This is the result. Therefore so T is norm preserving and it is also inner product preserving, therefore what we can say is let's find the angle now. Tx comma ty, the angle between them is cos inverse Tx comma ty, inner product of that, divided by the norm of Tx and Ty. Now since T is basically both norm preserving and inner product preserving, we have cos inverse of inner product of x comma y divided by norm of x, norm of y, and this is basically the angle between x and y. So this part is proved, and we need to prove one more part, which is the angle between x and Tx is theta. That is, to find that out, we know that the angle between x and Tx is given by cos inverse inner product between x and Tx divided by norm of x and norm of Tx. So let us first find out the inner product between x and Tx. So the inner product between x and Tx is basically given by let me just find it out the traditional way, because we need to check the definition of Tx first again. So we found out that Tx was this matrix here, x1 cos theta plus x2 sin theta, x2 cos theta minus x1 sin theta, and x is given as x1 comma x2, so we can just multiply them together. So we don't need the summation sign here. So what we can do is this: we can multiply the first x1 into x1 cos theta plus x2 sin theta, x1 into x1 cos theta plus x2 sin theta plus x2 into x2 cos theta minus x1 sin theta. So it's x1 square cos theta plus x1 x2 sin theta plus x2 square cos theta minus x1 x2 sin theta, and this would give us x1 square plus x2 square cos theta, right? Therefore, the angle between x and tx being arc cos inner product of tx and x divided by norm of x and norm of tx is equal to arc cos. Now we know the inner product is basically x1 square plus x2 square multiplied by cos theta, and we also know that tx is non-preserving, so this is mod x into mod x. So this would give us arc cos. Now x1 square plus x2 square is simply norm of x whole squared cos theta, and the denominator is as well norm of x whole squared, so they cut off because they are positive, and we have arc cos of cos theta. Well, this is simply theta because 0 less than equals to theta less than pi, which is in the principal region. So this would prove our problem right here. This means that we have completed most of the problems here, so let us actually try to see what more problems we have so that we can do them in the next lesson. So in the next lesson we would be try to bound a linear transformation in terms of the input, and then we will try and start a new chapter which is subsets of Euclidean spaces. So this should be all, and the supplementary notes are given inside the video as you have already seen, and those supplementary notes would include some basics of derivatives, so you would see that. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.